The second talk of the session, we have Jess Banks. Jess is, I think, a student here currently.
Yes, yeah.
Yeah, I don't know how it can be because Jess has been doing awesome work for so many years. But yeah, Jess is here to talk about refutation and spectrally quiet planting of cuts and colorings in random graphs. Take it away, Jess.
Thanks, Sam. Yeah, thanks for that introduction and, of course, for the invitation to speak. So I've been following along with the workshop remotely for the last couple of days, so it's very nice to be here in the flesh with you all. This is some joint work with Afonso Bandera, Tim Kniske, Christopher Moore, and Alex Wine, three of whom we're obviously lucky enough to have in the room today. I promised cuts in random graphs, and instead I'm just going to tell you about colorings because time is precious here on this earth. So let's get moving. Okay, as usual in life, we have a null model, uniformly random deregular graphs for the next half hour. We have a planted model, which I'm not going to commit to the specifics of, but it's just some k-colorable distribution over deregular random graphs. I know that these little things are going to be wiggling around the screen. I just want you to know that I know, and it bothers me as much as it's going to bother you. So the talk today is about the interplay between two different algorithmic problems related to these two different models. One is decision, telling them apart, and the other is refutation, which doesn't care about the planted model at all and just is trying to prove that the null model is not k-colorable. So as we've heard a lot already this week, these problems are quite related. And in particular, in general, if I have an algorithm that can refute the existence of k-colorings, it also gives me a decision algorithm that works to distinguish the null model from actually any planted model I could care to choose, so long as we're in a regime where the null model is not k-colorable with high probability. So, we've heard lots of great techniques for proving hardness of decision this week. And the point here is that all those types of evidence also can give you evidence of hardness of refutation. But that this requires that you be a little bit choosy about which planted model you talk about. So you want to choose a quietly planted model, one that's hard to distinguish from the null model, and that will give you better evidence for hardness of refutation. So that's what we're going to do today. We're going to design a computationally quiet planted model and give a little bit of evidence for hardness of decision. And in the paper that I'm talking about, we talked about some very basic kinds of evidence for hardness of decision. We just computed the Keston-Stigum threshold, very simple thing to do. We also studied this local statistics hierarchy, which was introduced in a paper of mine with Siddhant, who's in the audience, and Prasad, who I think is not. So the idea is it's like a semi-definite programming hierarchy for decision problems that is indebted to all of the lovely work on pseudo calibration and sum of squares that many folks in this room have worked on. Okay, so that was the stuff in the paper. And just to make things simple, for the talk today, I'm actually going to do something even more basic. Let's just think about when can you plant k-coloring in a deregular random graph so it doesn't mess up the spectrum. So the spectrum looks like a uniformly random deregular graph. So I'll just remind you, this is what the spectrum of a deregular random graph looks like. There's some eigenvalues which are kind of confined to this interval between -2 root d minus 1 and 2 root d minus 1. There's a trivial eigenvalue at d, and there's basically nothing else. Okay. So this is the plan. Any questions about this? Okay, so I'm contractually obligated to show a phase diagram. So here it is. Here's D, here's K. When K is big enough, both decision and refutation are impossible because the null model is just k-colorable with high probability. On the other hand, when K is sufficiently small, less than around root D over 2, refutation is easy. You can do kind of a spectral refutation thing, which I'll tell you about on the next slide. And so there's this big kind of wedge in the middle here where we think refutation might be hard. And the whole game today is going to be to give some evidence that that's the case. Okay, but first, just to get us all limbered up, how does spectral refutation work? Well, here's how it works. So let me define this quantity MCK, which is like the normalized max K cut in the graph. Okay. Just the maximum over all labelings of the vertices of the fraction of edges that have different labels. So if MCK is equal to 1, the graph is k-colorable. If it's less than 1, it's not. So there's some work of Hoffman in the 70s that you can kind of retcon into being an upper bound on this max K cut. Here's what the upper bound looks like. You get this bound kind of in terms of the smallest eigenvalue of the adjacency matrix. Let's just remind ourselves how this works. So let's say I have some partition of the vertices into K groups, and I'm going to define this matrix P sigma. Sigma is the name of the partition. It's indexed by the pairs of vertices in the graph, and the UV entry for vertices U and V is 1 if the labels are the same, and it's -1 over K minus 1 if the labels are different. It's a PSD matrix. It has trace n. It has some other nice properties. And now, just by glancing at this, you might imagine that the inner product between this matrix and the adjacency matrix will tell you something about how many edges are cut by this partition. And indeed, it's true. So here is how you write MCK in terms of these P sigma matrices. And because P sigma is positive definite and has trace n, you can bound this from above by this smallest eigenvalue of the graph. Questions here? Great, we're cruising. Okay, how do you use this to get an upper bound on MCK for the planted model? Well, this is the kind of thing you get. And you get it just by combining this Hoffman's theorem from the previous slide with Friedman's theorem about where the eigenvalues, the adjacency matrix of a random irregular graph lie. In particular, that the smallest one is at most 2 root d minus 1 plus a little bit of extra stuff in absolute value. And so, of course, this rules out K colorability whenever this right-hand side is less than 1, which happens when K is around d over 2 root d minus 1. Okay, so that's the story of this bottom line in the phase diagram. And so now we actually have to start thinking about what's going on in the middle here. And I promised at the beginning that we would, generate some evidence for hardness of refutation by studying different decision problems with different planted models. So let's first see what happens if you take the very boring garden variety planted K coloring model, which I'll remind you the specifics of on the next slide. So what happens is that when K is around root D, that's the easy hard transition for distinguishing these two models. So above there, we think that decision is hard, which supplies some evidence that refutation is hard. And below it, we think that decision is easy. In fact, we know so because you can just do it using the spectrum. I'll say why that is in a second. But the point is that this leaves open this whole kind of lower wiggly triangle here, where this planted model is not supplying any evidence for hardness of refutation. Okay. And so to design a better one, let's see why this one fails to do it, why it's not spectrally quiet in this range. So here's how this model works, in case you forgot. I start off by dividing the vertices into some different groups, and I just sample a deregular random graph conditional on there being no internal edges to each of those groups. So conditional on those groups being a valid coloring. And if you look at the spectrum of one of these things, what you'll find is that it kind of looks like the spectrum of a random deregular graph. So there's this bulk of eigenvalues between these two familiar numbers. There's this trivial one at D. But then as soon as K is less than root D, a bunch of eigenvalues leave the bulk. Sad. So you can just look for these things and easily distinguish. Okay. So to kind of give some intuition for why this is happening, let's take a detour into another weird world of continuous probability. And think about the following problem. So let's say I want to design a Gaussian random matrix whose spectrum looks kind of like a Wigner matrix. So it has this usual semicircle distribution, but I've pre-selected a vector v and a number lambda kind of close to the lower edge of the spectrum. And I want this quadratic form to be around lambda for my pre-selected vector v. Okay, how do I do this? Well, one option is I just sample a Wigner matrix and I spike it with a rank 1 matrix. But you shouldn't do this, or rather, you shouldn't expect that it'll be quiet, because there's some work from about 15 years ago that says that as soon as lambda gets close enough to the bottom end of the spectrum, this thing ejects an eigenvalue that lets you tell it apart from a Wigner matrix. Okay. So that's a bummer, but luckily there is a different thing you can do, which is the following. So again, you can sample a Wigner matrix, but instead of just kind of doing this like crass add a rank one matrix thing, what you're going to do is, go to your number lambda that you want. The eigenvalues of this Wigner matrix you sampled are pretty nicely distributed in this interval -2 to 2. So you can find one lambda hat that's approximately lambda, and it'll have some eigenvector rather v hat. And now you're going to set your planted matrix X to be U times W times U star, where U is a unitary matrix that maps V hat to V. So in other words, you're going to rotate things so that V hat is actually an eigenvector. Sorry, V is actually an eigenvector of the sampled matrix. And this is great because, of course, the spectrum is the same as the matrix you started with. You just rotated by a unitary. But now you've guaranteed that this quadratic form is exactly what you wanted. So this is a nice observation by Afonso, Tim, and Alex from a little while ago. And the lesson here is that if you're going to quietly plant some signal and some matrix, it's good if you can arrange things so that signal is itself an eigenvector. And there's a very nice way to do this in the continuous case when everything is kind of rotationally invariant and you can just pick this unitary. But what are we going to do in the case of deregular random graphs where things are much more like combinatorial and brittle? Okay, well, I'll tell you what we're going to do. We're going to look at random lifts. So there is a lot of nice technical mathematical stuff you can say here, but let me just tell you the layman's version of a random lift. So let's start with some graph H. Here it is. Maybe it has some multiple edges. That's okay. Let's also assume it's k-colorable, although you don't need it to be to do this random lifting thing. And now to make our random deregular graph G, we're going to blow up each of these vertices of H to a big cloud of vertices. And for each edge of this base graph H, we're going to add a random perfect matching between each of the clouds of vertices. So if there's multiple edges, then we'll add multiple matchings. If not, we'll just add one. And there's a couple of important things to say about this. One is that if H is k-colorable, G is k-colorable too, right? Because you can just lift the coloring up from the small graph to the big one. You want to see that? Okay, the other nice thing is that locally, this graph G looks exactly like H. So every blue vertex is connected to two pink ones and one yellow one, etc. And because of these properties, you can show that all of the eigenvalues of H actually lift to eigenvalues of G. So this is kind of neat. And moreover, it is a consequence of a much bigger and badder theorem by Bordunov and Collins from a couple of years ago, that all of the rest of the eigenvalues of this random lift G look exactly like a graph from the null model. So, in other words, if you look at the spectrum of G, there are going to be some eigenvalues, these yellow ones coming from the base graph, and then everything else is just this usual shape that we have. So all of that is to say that as long as the eigenvalues of H are inside this interval, as long as H is Ramanujan, then this model is spectrally quiet. Its spectrum looks more or less like the spectrum of a uniformly random deregular graph. Okay. Any questions about this? So this is going to be our planted model, our quietly planted model. And now we just have to study this for various choices of this base graph H. So in the paper that is the subject of this talk, we picked a very simple kind of base graph H. So let's assume that k-1 divides D. And let's just take H to be a graph with k vertices and a bunch of multi-edges between each pair of those k vertices, so that there's the same number of multi-edges between each pair. Okay. So this, if you take a random lift of this, it goes by another name. In fact, many other names in the literature. It's kind of annoying. The equitable stochastic block model, or the regular stochastic block model, or the whatever. Everyone calls it a different thing. But the property is that each of these vertices that arises from a blue vertex is connected to exactly the same number of all other types of vertices. So it's kind of equitably, whatever. It's equitable, I guess. And in our paper, we show a couple things about this model. So in addition to it being spectrally quiet, we show that whenever k-1 divides d and k is larger than this familiar number from before, a couple of things happen. So one is that the trivial fixed point of BP is stable. So in other words, this is like the Kestensingham threshold for this model. We also show that low degree local statistics, which is this SDP hierarchy that I mentioned but did not explain before, fails to solve this distinguishing problem between this planted model and the null model. So this is some kind of rudimentary evidence for hardness of distinguishing. So this is kind of neat. But of course, this model is only defined for certain values of k and d, right? So going back to this region of interest here, all these blue dots are places where like k-1 divides d. And so, if d has lots of factors, then there's lots of k's for which this could happen. But if like d is a prime number, then this model isn't defined. And so we actually haven't provided any evidence for hardness of refutation because there is no quietly planted model to speak of. So the question is like, what's going on for other values of d? Like when d is prime or d is small or whatever. So what we're working on now, since we're among friends, I'll tell you about some work in progress. So the claim is that if H is any deregular k-colorable Ramanujan graph, then the same two things as before hold. The trivial fixed point of BP is stable, and low degree local statistics fails to distinguish these two things. So this would provide some more evidence that for lots of other values of D, something is going on with hardness of refutation. And so motivated by this, let me make a conjecture. The conjecture is this. This condition of there being a deregular k-colorable Ramanujan graph is exactly what is controlling hardness of refutation for this problem. So whenever there's a D and K for which one of these things exists, then it's hard to refute. And if there's not, then it's easy to refute. So if you know anything about Ramanujan graphs, this should disturb you a little bit because they're notoriously difficult objects to study or to prove the existence or non-existence of. So I think it's quite striking, actually, that they're showing up in this problem of refuting colorings in random irregular graphs. So I'll leave you with that conjecture and then just a couple of things that either I or even better you all should do. I'm surprised no one shouted this out, but I'm cheating a little bit with this planted model because although the spectra look the same between it and the null model, you can tell the two apart just by looking at all the eigenvectors. Because in fact, the eigenvectors of the small graph lift to eigenvectors of the big graph that have a very specific structure. And so, okay, what's up with that? Well, maybe you can just flip like linearly many edges and this will go away. This also happens in lots of other situations, right? Where things like sum of squares can't see things like this. Like Gaussian elimination succeeds, but we also think the problem is kind of hard or whatever. Okay, so someone should maybe study this model. It would be good to give other evidence, more substantial evidence that decision is hard between this planted model and the null model. In particular, I don't know, higher degree local statistics or like low degree polynomials, although these are both pretty notoriously challenging in this case of deregular graphs. On the other hand, it would be good to just study other refutation algorithms like higher degree SOS or other types of improvements to Hoffman's bound. This is something we're thinking about as well. And then finally, I think the most interesting next question is, how do you do this in the case of like non-regular graphs? So let's say you wanted to quietly plant a coloring in a sparse Erdős-Rényi graph. How would you do so? Because there's no natural analog of this like random lift in that case. And so it, I think, is a really nice question, and I'm not quite sure how to answer it. Okay, so there's lots of homework for all of you. I hope to see the assignments on my desk soon. And with that, I will go back to the title slide and take some questions.
Yes.
So on the last point about Erdős-Rényi graphs, does the lower bound work on Erdős-Rényi graphs?
The
Hoffman thing.
So you can do a different thing that involves looking at the spectrum of the non-backtracking matrix. But because the adjacency matrix of Erdős-Rényi like sparse graphs looks kind of smeared out along the edges. That specifically doesn't work, but there is another spectral refutation.
This construction applies for larger D, like D going with N.
Yeah, it's a good question. I haven't thought about it.
This conjecture that you mentioned about hardness when like there exists or doesn't exist a deregular graph, that's up to a factor of 2, right? Like things are still okay.
How do you mean?
The threshold for refutation that you're talking about is trying to improve in this factor of 2, or
Yeah, that's right. I mean, the conjecture is that literally if I fix some value of D and I want to know which values of K one can easily versus not easily refute K colorability, that it suffices to check whether there does or does not exist a K colorable range.
So if there doesn't exist one, I mean, okay, proving that there's no polynomial sum algorithm, okay, fine, we're not gonna talk about that. But if there does not exist a Ramanujan graph, do you have any faint idea of how to turn that into an algorithm?
Yeah, so I mean, in some sense, in some abstract sense, so, let's say you look at all possible deregular K colorable graphs, and you look at, board space. So, here's a -2 root D -1. Let's say you look at all possible deregular K colorable graphs and you look at where their smallest eigenvalue is. So there'll be a bunch down here. If there's some separation between this and -2 root D -1, and you actually prove that, like you prove a lower bound on, how far to the right these lambda mins go, then that gives you a refutation algorithm. And you just check whether your graph has an eigenvalue smaller than that. So it's not a crazy notion that this could actually be conformist. I mean, there's lots of weird potential cases where, like, there's no Ramanujan graph, but there are ones arbitrarily close. I don't know. Yeah. Seems complicated. I should say there are similar results for like large K-way cuts and deregular graphs too. Similar protections.
Okay, let's thank Jess once more. Let me remind everybody that tomorrow afternoon, Michael Celentano is leading a